Test-time adaptation has become one of the most promising ways to keep neural networks robust when they encounter real-world distribution shifts. The idea is straightforward. Instead of relying on offline retraining, the model updates itself on the fly using incoming unlabeled test data. But there is a fundamental bottleneck that keeps most TTA methods from reaching edge devices. Standard adaptation relies on backpropagation. And backpropagation is brutally memory-hungry. You need to store the computational graph, intermediate activations, and loss gradients for every parameter you update. On a mobile phone, an IoT sensor, or a quantized edge accelerator, that memory footprint is simply not feasible. So how do you adapt a model when you cannot compute or store gradients? The answer lies in combining three ideas that on their own have limitations, but together create a surprisingly efficient pipeline: Zeroth-Order Optimization, model merging, and cross-device collaboration. Let's start with the framework. The authors operate within a cross-device collaborative TTA setup. In practice, this means you have a network of devices with varying compute capabilities. Some have enough RAM to run traditional gradient-based TTA and produce adapted model weights. Those weights are shared back to a central server or directly to resource-constrained devices. The challenge is how a low-memory device can actually use those shared weights to adapt to its own test distribution without running backprop. The first pillar of the solution is Zeroth-Order Optimization, specifically a variant called ZO-SGD. Unlike gradient-based methods, Zeroth-Order Optimization only requires forward passes. It estimates gradients by perturbing the parameters in random directions, running 2 forward passes to measure the resulting loss difference, and then updating the parameters in the direction that improves performance. Mathematically, you sample a perturbation vector z from a normal distribution, add and subtract it from your parameters to get phi plus and phi minus, compute the loss difference s, and update using a pseudo-gradient proportional to s multiplied by z. This completely bypasses the computational graph and activation caching. The trade-off is that zeroth-order methods are notoriously noisy and struggle in high-dimensional spaces. Optimizing millions of weights, this way converges too slowly to be practical for test-time adaptation. That is where the second pillar comes in, model merging. Instead of optimizing the full weight matrices, we reframe the problem. Each adapted model from the network is treated as a task vector, which is simply the difference between its weights and a shared base model. We combine these task vectors using a set of merging coefficients. Now, rather than optimizing millions of individual weights, we only optimize the coefficients that control how much each task vector contributes to the final merged model. This drastically reduces the dimensionality of the optimization problem, making zeroth-order optimization actually viable. But raw model merging has a hidden flaw. Task vectors contain a lot of noise. Some weights are completely uninformative for the adaptation task, and when you merge multiple models, their task vectors often point in similar directions, creating redundancy. If you just average them or optimize coefficients naively, the interference degrades performance. The paper solves this with a 3-step preprocessing pipeline that runs entirely on the server side, so edge devices never pay the computational cost. First is non-influential weight suppression. The authors apply a top K filter to each task vector, zeroing out the smallest magnitude weights. This removes parameters that do not meaningfully contribute to the adaptation signal, reducing interference between models. Second is redundancy reduction through low-rank approximation. When task vectors come from similar domain shifts, they become highly correlated. The method concatenates all processed task vectors into a single task matrix and applies singular value decomposition. This compresses the correlated information into a lower dimensional subspace. Instead of optimizing one coefficient per model, you now optimize a reduced set of coefficients that operate on the compressed basis vectors. Third is adaptive rank selection. Not every layer or weight group benefits from the same amount of compression. The algorithm automatically selects the optimal rank for each weight group by monitoring the reconstruction error of the SVD approximation. It picks the smallest rank that keeps the recovery error below a predefined threshold. This ensures you are not throwing away critical adaptation information, while still minimizing the number of coefficients you need to optimize. Now the edge device receives the compressed task matrices and initial coefficients. During test-time adaptation, it reconstructs the merged model weights on the fly, runs forward passes to estimate loss differences, and updates the merging coefficients using ZO-SGD. But there is still a memory problem to solve. Storing the random perturbation vectors for every optimization step would require memory comparable to the model size itself. The authors solved this with a clever memory trick, the random seed trick. Instead of caching perturbations, the device sets a fixed random seed, regenerates the exact same perturbation vectors on the fly, uses them for the forward passes, and immediately discards them. This keeps the memory overhead almost identical to standard inference, which is critical for deployment on constrained hardware. The results validate the approach. On standard corruption benchmarks like CIFAR-10C, CIFAR-100C, and ImageNetC, as well as style-transferred datasets, this method consistently outperforms existing gradient-free baselines like batch normalization statistics updates, prototype shifting, and prior collaborative merging approaches. The memory footprint drops dramatically, often down to roughly a fifth of what backpropagation-based TTA requires. And because the method does not rely on gradient computation, It works seamlessly with quantized models, where traditional backprop is mathematically unstable or entirely disabled. This opens the door for real-time adaptation on heavily compressed, edge-deployed networks. Let's be clear about the trade-offs. The accuracy still does not quite match full backpropagation TTA. That is expected. Zeroth-order gradient estimates are inherently noisier, and restricting adaptation to a low-dimensional coefficient space limits the model's degrees of freedom. The authors acknowledge this and point toward hybrid approaches as the next logical step, dynamically splitting parameters between gradient-based updates on capable layers and zeroth-order updates on others, tailored to the device's memory budget. It is a promising direction for balancing accuracy and efficiency in production systems. This research tackles one of the biggest bottlenecks in deploying robust AI at the edge, the memory cost of on-the-fly adaptation. By synergizing zeroth-order optimization with model merging and smart preprocessing, it proves you do not need gradients to adapt models in real time. You just need a smarter optimization landscape. As edge computing and domain shift adaptation become standard in production AI, methods like this will bridge the gap between theoretical performance and real-world constraints. If you are working on efficient AI, test-time adaptation, or edge deployment, this is a blueprint worth studying. Thanks for watching, and I will see you in the next one.